All right, 11 o'clock on the button. Everyone. So I'm Tom Daugherty with Triple Point Environmental. A couple slides here, just company intro, then we'll get into some food processing stuff, a little bit of Aeration 101 before we get into the food processing. I'm actually at a job site right now at an apple processor. I was there this morning and froze out to come back to the hotel room to do this webinar. Background wise, I started out as a mechie, did not finish as a mechanical engineer, but been in the water space for about 20 years, shared office with a PhD for 7 years. So I got my in the trench training there, but nothing formal on the engineering side. Did go on the business side, and I'm actually a general contractor. I do a lot of triple points installations, sometimes assist, sometimes do construction observation. Just finished one up in Eagle, Idaho for a municipality. It was that sort of a job. And I'm a licensed wastewater operator. Get the screen to advance here. There we go. So quick thing about triple point, just soup to nuts in a lagoon space. If you've got a trickling filter or an activated sludge plant, we don't have anything for you. But it's lagoon-based treatment, which we see a lot in the food processing side. We do aeration to ammonia removal to nitrogen removal and some phosphorus removal across the board. That's our space. So things I want to touch on today here are just we'll talk about Aerator that we used for a bit, get into a little bit of Aeration 101, installation challenges, case studies, and yes, a blower fire at a brand new installation. And I have a lot of cool pictures of that blower fire and the forensic investigation of why we had that fire, what was the remedy, and I want to share that as a lesson learned. I think it's very interesting. So aeration, just at the high level, is all about giving oxygen to the metabolizing microorganisms and providing mixing. It's just the two things. We're putting oxygen for the bugs and we're mixing things up. You got to keep things mixed up so the bugs can get to the oxygen. So just another high-level understanding in the lagoon space about treatment levels. I want to just cover real quick with this slide. You have a facultative lagoon, which has no airflow, just natural. And you can get a lot of airflow from natural, that upper portion. Humidity and wind is your friend when you're in the lagoon business because air will infuse DO in that, especially that upper 18 inches. And the standard reaction rate for a facultative lagoon, you do get treatment. And you can see that those values in the right-hand column. And then we move to a partial mix lagoon, and generally that's defined as 2 to 5 standard cubic feet per minute per 1,000 cubic feet of volume, and you attach a reaction rate to that of 0.28 when you're doing your calculations. Then there's a not well-known mix that we learned from an engineering firm some 10 years ago in the West, and the one I just mentioned earlier, just installed in Southern Idaho, which was a municipal, uses a vigorous mix there that was engineered by Jacobs, is 7 to 8 standard cubic feet per minute per 1,000 cubic feet, and you get your reaction rate of 0.85, so it's a little bit more reaction going on. And then a complete mix is almost an order of magnitude more than partial mix. That's everything is in suspension. You know, it's 10 to 15 standard cubic feet per minute, and then you can actually mix RAS too, and that just takes quite a bit more air. RAS, return activated sludge. So just a profile view here, I'm kind of going to parallel a typical surface aerator versus the aerator that we use a lot and have good success with in food processing. Is we release air about 9 inches off the bottom. So you destriate the entire column and you mix and you pull in from around the aerator up through a central tube. I got another slide that will show that a little better. Oftentimes with the surface aerator, you're kind of limited here you don't get quite as much mix zone. Again, here that this is a cross-section profile of the aerator, and this is a hollow tube, and we pull up inside the hollow tube and get solids up into the treatment column, and we're able to reduce solids quite a bit by this sort of mechanism. Here's some of the shots of computational fluid dynamics work that we have done. Key thing to understand about this aerator is these are all fine bubble radiuses here, and we have a coarse bubble inside that is for mixing. I'm going to get into the sizing of fine and coarse bubble in a couple slides from now. The coarse bubble is about 10% of this flow and gives us a really good mixing, and we get to real good transfer efficiency by these diffuser tubes, fine bubble diffuser tubes. Just a closer up view here, and in this view, only takeaway is that we push these tubes in, and with a quarter turn, they're in. They don't have to screw on for multiple screws. That was the old school way of doing it, and this is a quick disconnect. And contractors really like this, putting them together, because it's very, very quick, especially when you're doing 20, 30, 40, 100 of these things. Each of them has 10. That's a lot to put in there and do it right. These have a click mechanism. When you push in, turn it, and click, you know it's done. You don't have to reef on. It's done by bare hand. There's no tool. So this slide, if we were just traveling up an elevator, sitting having coffee, it would probably be the slide I would use to explain how the subsurface diffused aeration works, and the way Triple Point does it, and other companies do this as well. You know, more or less, we've got a positive displacement blower on land. We convey air through a header over to a manifold system. The manifold system above shore feeds the aerators by flexible weighted line out to each aerator with individual ball valve. Each one of those could be turned off. In this instance, this graphic, this one's turned off, and maybe they're pulling this up to do maintenance on it or installing it initially, and we can turn the air off right to that one, which also allows you to move air around a little bit inside a lagoon if you want a little bit more air to the front or the back for some reason operationally. As time goes by, you have that capacity with these ball valves on shore. Now, when we get to in excess of 50 aerators, we'll often go to a lateral system and may not use the individual ball valves. We may just shut off individual laterals, floating or weighted to the bottom. And I'll show an example of weighted to the bottom coming up. Just another engineered drawing view, buried header going up to the manifold, that flexible weighted line, which really brings a lot to the party. It'll go over an undulation or a turn, and it is weighted and designed to sink. But it's 1.5 inch inside diameter, and it's able to convey air and go over any, if there was a tire in the bottom or something, it'll just go right over it and get out to the aerator. And this is just some of those, some of that hosing on pallets, it looks like when it arrives. Now, this location I'm at, it's cold, and they actually took these into some warehouse to warm them up. But once you get them pulled out, I say pull them out and get them out in the sun a little bit, and they'll lay just like this. And then we cut the proper lengths and convey from the shore out to a location. This on the right-hand side was, I showed up at a job one time, and I told the contractor to get it all laid out in the sun, and they had a couple of their laborers did this and kind of left a rat's nest of it, which had to get, this is a downhill bank there too, but we got through it. So there are typical acronyms used in every business, and most of these are probably familiar to a lot of folks. I'm going to look at SAE here in a couple subsequent slides. SCFM we use, standard cubic feet of air. You can see the rest. So in the in the efficiency space of aeration, it comes down to pounds of oxygen per horsepower per hour. So if we looked at a mechanical surface aerator, you're looking at approximately 2.5 to 3.5 pounds of oxygen per horsepower per hour. If you went up and looked at a fine bubble diffuser, you were looking at approximately 2x of that at 6 to 6.5 pounds of oxygen per horsepower per hour. This is significant to look at because we see a lot of mechanical surface aerators. That's why I'm isolating on that. And this is kind of where we fall in, and others with fine bubble treatment. It gets significant because of potential savings of power. So if you're running 100 horsepower and you can a surface aerator, maybe you can get that done for 50, 60 horsepower of subsurface aeration. And then the utility company will say, okay, you're going to save that power permanently back to the grid, and we'll do this formula and offer you an incentive for making this upgrade, which doesn't pay for CapEx, but it'll offset CapEx to a degree. This site I'm at right now, which happens to be an Apple processor, is actually going to get, they're taking surface aerators out and putting the subsurface diffused in, and they are going to get a rebate. And we just finished that with a sugar beet processor too, got a pretty significant rebate. It correlates obviously to the size of the operation. Now, looking at the same standard aeration efficiency, but we put depth on the x-axis here. So if we take a look at a high-speed surface aerators example, when you're more shallower, they work better. You get a better transfer because they reach the bottom much easier. But if you start going up to something deeper, 11, 12, 15, 16 feet, it gets to be a little bit more challenging. So you go back to the coarse and fine bubble aeration, anywhere from 7 or 8 feet up to 18 feet, you're playing in a pretty good area. Now, I will note that of all of these technologies, the SAE test, which is developed by the ASCE, the Civil Engineering Group, are conducted in clean water at zero elevation, so everything gets derated for the constituents in the water, whatever situation you are in. So that's linear pretty much across the board, but it isn't exactly 6. If you're at 3,000 elevation dealing with 3,000 BOD, it would be something less than that in all these situations. So a couple more 101 statements. O2 is known to oxidize things like H2S, hydrogen sulfide. And I like that point because that's generally considered it's a chemical reaction. That's not a long, we're doing biology and we got to get it up and going for 3 weeks to 6 weeks to get it acclimated. And it's the same with the bottom bullet there on metals. And there's academic papers that support this, that O2 transforms metals, such as iron and manganese to an oxidized state. These are reactions that occur pretty much when you expose, fine bubbles to these constituents. And this slide is just, if anybody fell asleep yet, this was a methane capture. This is actually a true research project in Australia to methane capture, but nothing to do with this presentation. I just see if everybody awake yet. So getting on to bubble size, all these 3 graphics are 1 cubic foot of air, one cubic foot of a bubble, of volume. So on the left, that's a 12-inch bubble. Think of a basketball as 9 inches, so that's 12 inches. So we look at the surface square feet of that is 4.8. Now, if we go to the middle view, and we consider those 6 inches, half of the 12, that's 185 square feet. Now, I said I was going to say definitions. This is where we'll talk about the definitions. Coarse bubble is considered 4 to 6 inches. Literally, 4 to 6 inches is standard acceptance in the industry of a coarse bubble. And if we go to the right, what we're depicting there is a fine bubble. And fine bubble are measured in metric or in inches, it's generally considered 1/8 to 1/4, so quite small. So you take that same volume, now look at the surface area square feet you've got, 1,800 square feet. That's where you get tremendous oxygen transfer. You get good mixing with your bigger bubbles, your 6-inch of coarse bubbles, but the oxygen transfer is significant when you look at the surface area of those. Also, when we talk about chemical reactions, and I don't go deep into this in this slide, and there's others that are way more capable of discussing it, but there's an electrical charge on the surface of those. That's why you get this foaming. And I'm going to show some foam pictures that occurred like within hours to overnight. They're just incredibly significant. When you have nothing in the water and you put in fine bubbles, you turn that on, there's reactions that begin going on right now while the biomass begins to build itself and acclimate over a period of time. So another thing about depth and bubbles is retention time. They hang out more. You know, back to that earlier slide, there's some folks out there that are working on nano bubbles or micro bubbles, and I think that's cool because I love R&D. And at this point, best I know, they're pumping water up to a dike or inside a building and treating it and returning it to the pond. And they get to these nano bubbles that they don't particularly rise, they just hang out. And I think that's a smaller flow application, but I think it's kind of cool if they figure that out for bigger flows. That's going to be very interesting. But right now, it'd be very difficult to transfer nano bubbles through a piping system down to the bottom of the pond. It's not practical at the moment. But depth and rise time and bubbles hanging out in the body of water is they spend more time hanging out when they're smaller. It's to shorten the thought on that. So as I've been kind of building up to this aeration, when you pull into this central tube and you have this somewhat of a suction or migration or Brownian movement to get over and go up through that tube, we get that kind of silt and that murky sludge on the bottom pulled up into the treatment column, and then the volatile fraction of that is bioavailable, you know, based on this data right here. And this is some of this data I borrowed from Steve Harris. It's not his entire slide, or I should attribute it to him, but most of sludge is made up of carbon, oxygen, nitrogen, hydrogen, and then a handful of those other components, and most of that is available. And Steve always says, mass to gas, mass to gas. In the right hand, in the picture right here, it didn't occur to me until I was looking at this presentation a while ago that the relevance of that picture, that's a Sludge Judge, and that was at a site, a municipal site in Montana. And the problem statement was out of their third settling pond going to constructed wetlands, they were holding 0 DO. And I remember asking the engineer and the site operator, how much sludge do you think is in that pond? And they guessed about 1 foot, which would be this demarcation right here. And they didn't have a Sludge Judge. So I bought one and went over there, went out in the boat, and I did a full grid. And I says, you've got 4 feet of sludge in there. And of course, it's less viscous up here as it is down on the bottom, but it would run right out. So it was a runny sludge. It wasn't a compacted hard on the bottom or anything. And so what do we know? Solids consumes oxygen, sediment oxygen demand. So it's pulling all the DO out down into the solids. So he lost these DO. And so we ended up putting some air in there, and this significantly reduced the solids in there. We did some checking over time, and now their DO jumped up to 5, and so they were getting too much air in there. So then they ended up putting their little 10 horsepower blower for this little pond, this little town in Montana, on a timer, and got it dialed into where they wanted to. But again, just an example of here's all this solids, and that's where your oxygen demand goes. And then in the food processing, that generally you tell that by odor. It just starts smelling. Again, stir that sludge up, get it up into the treatment portion, and let the biomass consume it. And that earlier slide, I mentioned a volatile solid. I put at the bottom said volatile solid, total solid, and go back. Down here, sample for volatile solids and total solids. I've just got a guy pulling some samples right now, and I pulled these myself in Central Coast at a winery I was at down there. And the volatile solids fraction, so you take a sludge judge like that, you go out in the middle of the pond, you get a solid sample, and you call the lab and tell them you need the bottles, and you take the actual solid mud sample to the lab and say, tell me my volatile solids and total solids. And they send that number back to you. And that volatile solids fraction, if that's 65, 70, 75, 85%, a lot of that solids is available to be converted to gas by subsurface aeration versus dredging and pumping and dewatering. So another small site, this was an interesting, back in 2018, we did this sludge buildup odors. The new lagoon was too shallow. So it was a brand new lagoon and actually only made it about a year and started having bad odor problems. And it was too shallow. I mean, they built it for 5 feet, but it was evaporative and there was no air. And so there's no allowance for that BOD load coming in there. And when somebody uses BOD, when I say BOD or COD or any of them, the key thing to me is the last 2 letters of the acronym, oxygen demand. There was no allowance for the oxygen demand. So it's going anaerobic because it's consuming all of the oxygen, and then it begins to smell. And bad odors, and the wind blows it around, and so it wasn't a good situation. And so they started adding chemical. I mean, you can see there's no grass even growing yet. This thing's a year old, and now they're adding chemical. And then in these buckets, they got little packets of bacteria, and they would walk all the way around and just throw them out in there to try to get something to grow. But again, they're only relying on the oxygen coming from the surface because it's a facultative lagoon basically to be evap, and kind of a tough design. And there's a bunch of fruit trees down below here, and I talked to the site. I said, if you go a little deeper with DEQ, maybe you can get permitted to sell your water and have a throughput situation versus being so shallow. And then they never did want to get up to 5 feet because they were worried about runoff and storm, and they didn't have no room to go, and they don't want to be spilling over the top. And it was kind of a tough thing. And so eventually they says, okay, we'll put some fine bubble in there. And I said, well, we're not going to be very efficient at 2.5 feet. Matter of fact, I don't have a solution for you at 2.5 feet, but they did it anyway. And this is me out on my boat taking this photo, and this is the installation. This water at that day we installed it was 26 inches deep, and it's just not very efficient. We sized it at 5 feet, and the amount of air to go down 2.5 feet is you got to almost cover the entire bottom at that point. But he was looking to mitigate because they had outdoor venue for weddings and stuff, and they just didn't want any odor. So we finally got it started up on May 18th. Again, your manifold's on your shore. This is winery process water. Hoses going out to it. You know, 12 fine bubble only aerators, because even a coarse bubble is not efficient there. It just gets to the surface quite quickly, and just off gases is air. And so you're just pumping air through to get rid of it. So we did fine bubble only. Now, interesting on the date here, notice May 1st, and let's go to the next day. So even as shallow as it was, and the solids we're starting to really foam this thing, because we're beginning to treat those solids that were just sitting in there. Again, there was nothing in the pond. We retrofitted, didn't even drop in from the boat. It was so shallow, the guys waded in hip waders, literally. And so you're starting to get all this foam, and that was a function of those initial chemical reactions, and it's starting to treat and do its thing as it's building a biomass in the background to get into more traditional treatment. So then we got the attention of some larger operators and says, okay, we're kind of drinking a Kool-Aid on this subsurface diffused air fine bubble, but we don't want it to kick butt and take names. And then 6 months later, we're dealing with foul diffusers, and all we do is spend all our time maintaining foul diffusers. So we came up with an experiment to show them a different diffuser materials and how we would evaluate that in their water. So we did one at a big sugar beet processor, another at a wine processor, and pretty much it was set up like this. We tested a standard EPDM rubber, which is these black ones are all EPDM. Silicone was the white looking one. And these all got the fine little tiny pinpricks in them that make those fine bubbles, those 1/4 inch to 1/8 to 1/4 bubbles. The polyurethane one is this greenish one. And then the rubber manufacturers have been talking about their different mixes. We can optimize one for sugar beet and we can optimize one for pulp and paper. And so we said, okay, this is a optimize, get a couple different of those mixes and we'll try them out. And then we did a coarse bubble control to the experiment. The coarse bubble is this one, just got holes drilled in it, and we know that's not going to foul. And so we went to this location, put a 30 horsepower blower, 8 aerators in the location. We're installing it here. We're putting there's that flexible weighted hose. These aerators with different diffusers on them, getting ready to go out. So then we devised how can we look at these underwater and evaluate them over a 6-month period. And so we come up with a rotometer method where we would run the air's coming in here, we turned our manifold upside down and welded it to this A-frame for this temporary pilot. And then we ran the air through this rotometer, and then this floating balls in here can tell us what the level is. So a close-up is here. So we can set the level by ball valve and we can equalize all these. And then the concept was the operator would do operator rounds and they would log each one of these. And they were numbered and say, well, item number 1 has 40, 40, 40. All of the materials did pretty good for several months. And then eventually we sorted out that actually the silicone oriented material was the best material, and we do use that a lot now. As a matter of fact, we almost default to it in municipal and in food processing unless there's something unique or different where there's a materials compatibility issue. But it was an interesting experiment, and we ran that at a sugar beet site for several months, and then we moved it to a wine location. And the irony of that one is we started out doing I told them, I said, based on my experience, I think you'll know what you need to know in 3 months. And it was also a paid pilot. They wanted us to come and look at it because they were looking to make a big CapEx move, but they wanted to, dig in a little bit, make sure they're buying the right thing. The site continued to rent it and rent it and rent it because the experiment itself was actually augmenting their process so well. Their pH was improving. Solids was reducing within the cell that we were in. We actually did a Sessi disc and sludge judging every 5 weeks for several weeks, and we just ended up going down, 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 down. And they kept renting it. But it was like a year and a half later, and they just keep renting it. So you guys are gonna, and then COVID hit, and so then they didn't have a very good direct-to-consumer business going, and they did not procure. But I think that they are pretty impressed with the system and made down the road. Another small one we did, and this is at the other end of the spectrum, like a 5,000 gallon a day guy wanting to go to 20,000 gallons because he's going to add different, more capacity. And he was using drip irrigation, so that was plugging. So he needed to clean it up quite a bit better. We went down there to a little pond, and I don't even think I made pictures of this one, but did a fine bubble, and they've been chugging along since 2018 down in Healdsburg. And then here's just this was out in Minnesota, and we've had some of these bigger operators come to Triple Point and say, can you just turnkey, do a design build and turnkey this? And so this is one of those that we turnkeyed. Now notice the concrete blocks here. They wanted the air on the bottom, which they got a header on the top, and these headers coming out on the bottom and just feeding air from the bottom. So we bolted them down to these concrete blocks in this clay basin. And then later looks like this. And again, right after startup, you get all this foam going. And foam's not new anywhere. We didn't invent foam, but when you see that foam within 24 hours of startup, you're cleaning some stuff up pretty good. There's a lot of reactions going on there. So moving on to another, this is another sugar beet one, and I showed this view right here because this was very challenging. This is the bottom of the lagoon, the sloped 2% slope, And so it's quite a bit deeper right here in the middle than it is over on the toe before it goes up to the top of the dike. So the second thing is they wanted to fill this, empty it down, fill it, empty it down, and treat as much as possible all the way down. Previously, their surface aerators, they could not turn on until there was 8 feet of water in this 11-foot sidewater depth pond. And so they had no treatment until it's, slow. Sometimes it might take six weeks to get up when they empty it down. So you got nothing going on for 6 to 8 weeks until it gets up to 8-foot level. Then they turn on these surface aerators and just pour the horsepower to it. And so they wanted to have a solution that allowed them to run air all the way down here, equalize pressure, don't damage the liner. The other design criteria is 12,000 milligrams per liter COD. They wanted less than 500 out the back. Their land applied to their own land. It's a large basin, 20 million gallons. It was going to be a dry installation. They wanted turnkey, one party. And so eventually, after various testing and meeting the folks on site multiple times, they decided to proceed with us, and we put it together. And these next slides will kind of animate that. So here you see that bottom, that taper where it holds water, and it's freezing because it's winter down here. And we begin to, it's been relined. Now, we didn't do the lining. We picked it up after it was relined. They had some erosion on a bank, and so they had to recontour that, took the old liner out, put the new liner in. And so don't damage the liner was, top of mind. They just spent a lot of money to put this liner in. So we end up doing concrete blocks, and we wrapped them. And I got some close-up pictures later, but we wrapped the blocks with other liners. So it's liner on liner sitting here. And interestingly enough, we hired a local contractor to place the blocks and do the wrapping and do this piping, a lot of fusing down here. And they placed all these. They put a big track hole here, and they put one over here, and they ran a zip line across. And they GPSed it. We GPSed this. They agreed. Our engineers agreed with the drawing, so they could pinpoint these things because these are heavy. Some of these blocks are, some of the big ones up here are hundreds and hundreds of pounds. And so they just moved down the dike on either side, and they zip lined out and set them right down in there. The most efficient way to get them in after the liner's been there. And it was very interesting. I don't know how many pictures of the zip line, but it's kind of cool. We later zip lined all the aerators. There was 152 aerators that went in here, and they zip lined all those too. So the air comes up and over and down, and they wanted bottom fed. Again, you're going to fill this up and drain it down, fill it up and irrigate it out, fill it up and irrigate it out. So each one of these side laterals coming in feeds two of these longitudinal laterals, I'll call them. For example, this one on this side feeds all the way across and all the way over here because they're just slightly higher elevation. This is just during some of the construction process. The closer up view of those pipes going out. Now these straps are intentionally loose because when they lower it down, it might sit there empty for a few days, and then the heat hits this HDPE and wants to move. So these straps were actually allowed to allow movement if it's completely drained down and sits out in the sunshine, or just the temperature change, as everybody knows how HDPE will move. Some other random shots of this was all designed by Triple Point engineers. The tapering, when you're running air over long distances, it starts out at a 24-inch header and eventually gets clear down to 4 inches at the farthest reach, but it's all tapered. There's orifices on all the aerators, so the pressure is the same everywhere when you turn this on, and that takes into account the slope. It's in the middle, it's deeper, and it's not as deep up on the slope. Here's that shows that distance again. This one's getting ready to be capped. There was a fusing equipment down inside there that did a lot of this work. And just some other angles of different parts of the construction. Of course, winter, now you've got aerators down here. There's just a short piece of hose coming off the takeoff on these submersed laterals, feeding those. Again, you see the water in the middle is, some of this is just from the snow melting and rain that may have occurred. It's getting deeper and deeper in here. And some of the final, I mean, you're wearing rubber boots towards the end in this thing, but just very little stuff to move. No ball valves down here. Everything's controlled up on shore as far as turning something on or off. Now this slide shows the depth in the middle. They're out of sight. Those tall canisters are out of sight on the aerators, and over here on this upper shore, they're sticking up quite a ways. So they have a mechanism via a ball valve or a butterfly valve set up. They can turn this top one off, but keep doing air when they've only got 3 foot of water, 2 foot of water, so they can really treat clear down to the nominal amount of water. And the overriding problem statement here was odor, frankly. Here's the blowers are set downgrade. Each of them had an arc flash spec here, so you got 2 separate panels running these 200 horsepower blowers. Air comes up over the dike and back down, and this is where they can valve off some of the different laterals down in the pond as it begins to subside. So they have an operational scheme where by VFD, they'll run 2 blowers at once, then they'll eventually shut 1 blower off as they begin taking water out. Then they'll go over and run the VFD down when it's way down to just the center of the pond, but they can actually keep applying air clear down to a very, very, almost a foot of water, because we're at 9 inches, and they can run it clear down that low. So they're getting a lot of oxygen and don't have to worry about odor too much anymore. And then when it's all said and done, it's a drone shot. This is the view, what it looks like, and it's meeting the effluent that we're looking for from 12,000 down to in the hundreds, going out to land app, and they drain it up and down. I went back on a couple visits when they drained it down. I wanted to look at it and observe it. They do know if they drain it down, they've got the diffusers out there and it's going to be a while that they must spray those off. They're toying with a method of not they only drain it down till it's above the diffusers, because if a diffuser gets out in the air and mud starts sitting on it, it will dry and potentially foul it. However, they have noticed a few times where that occurred, and it seems to scale up on these silicone. We did go with the silicone here and almost peel off like a hide on a snake or something. And so they're continuing to look at what they might do. They're also talking about making this more of a throughput pond, because they've got a lot of investment, a lot of treatment here, and they might treat from here and send it to a pond over here or another one adjacent. So moving on to a winery. Here was another greenfield winery situation, and I happened to tour this location in 2018, and I took some drone footage of its existing pond and these brush aerators right here, and a storage pond, and he land applies over here. So his design criteria to come in, he wanted 1 DO coming into this pond out of the new ponds. So as I was there in 2018, I actually happened to take some footage just elsewhere, and this is where the new pond is now, as you'll see in a subsequent photo. And then bottom screen here is the brush aerator pond. I just happened to take a picture of that and used it. So we helped them, and I wanted to mention here, this guy has a Headworks, and he does really well getting a lot of the shells and husks and stuff out of the water before it goes into the pond. And interestingly enough, he has on the order of 3,100 BOD, and most of the time we see 5,000 to 7,000 in a lot of the wineries. 5,000 is some of the engineering groups just say put that as a placeholder value while we're doing calcs until we can get another actual field sample, but he's pretty consistent around 3,100. I think a lot of that is he keeps some of this stuff out as a Headworks, just like you see in a municipal sewer plant. So here was one of the conceptual drawings. At first, I wanted to do 2 ponds, and we helped a lot with this. Matter of fact, we recommended the final volume. I told the operator, I said, look, if you're going to spend the money and do all the civil work, put a liner in and build it. Try to get double-digit days hydraulic residence time for whatever your flow is. You got double-digit days residence time. And so he eventually got with that. We went back and forth on the slope because he was going to a steeper slope. And I said, if you open that slope out, you actually gain this much more gallonage, which gains you residence time. Anyway, we eventually arrived at one single pond. We're going to put blowers up on by his headworks screens up here, and this was kind of our preliminary layout drawing for the site. And then we went ahead and he wanted it turnkey, didn't want to bring in a bunch of other folks. So we did a piping schematic for the site, which detailed the actual pipes needed to buy all the way, and the order of construction of all those pipes all the way through the system. And here was a bill of materials you needed to get, and he did all that. We did that as a value add for him, and he went and bought this from the pipe company and was able to save a little money on that, and we just helped him out in that regard. That's our bag day in, day out. So he had a crane on site, this massive crane. He says, we're just going to pick these up out of the lot and set them over there. And so here's one coming in on a strap right here. So we went out and put some tape down, and we're going to set all of these things. And you don't see a dry installation a lot. We did the other sugar beet one and this one. And so here's starting to take shape. We're sticking the area, don't have diffusers on them yet. We've run some of the hoses over the hill. The hose management was pretty difficult this site because it was tight quarters. So we would do it just in time, kind of, so we could stay ahead of the game. And then we just put the whole box of diffusers, because they had the crane there. We just picked them in, and we started distributing these diffusers just out, just piling them up over here. And then we'd go back and connect all of them. Here again is that flexible weighted hose, and then you had the beauty of looking at exactly where it wanted to go. Oftentimes we're on a boat, dropping stuff down on a pond, as we'll be doing at this apple processor I'm at. We've got a pontoon here, and we'll be out and come from the shore over to the location, and then we'll drop it. You won't be able to see it, but you can there. Hose management is a big thing here, but we got through it. Sometimes you just have to schlep hose. So here's a view again of across the pond. Everything's pretty much in position, and they started running water. Now we did taper this lagoon because he uses a certain chemical in there that he's able to pump it out from one end. He uses a chemical in the processing here, and you can see it starting to pool up at this end a little bit. And there it's pooling a little bit more. Now we're starting to get more water, and he started pumping in water on this end too, because we're trying to get enough water to turn it on while we're down there, because once you have all this in, and you've got to get it up, as me as the startup guy and the installation help, we got to get enough air over the top of these so we can vet it. And this was also very hot, 9,700 degrees out during this installation. And now they're starting to get a little deeper, but you can see the taper. These back here are still above water, but down here they're below water. Intentional design. And we first turn a little bit of air on just to vet everything. And then eventually he gets it up to 11 feet. And I wasn't there when it got to 11 feet. I left the site, and it took him, I don't know, several weeks to get it completely that full. And he sent this picture. He called up and says, this thing is really foaming. They turned this air on with all this water. I said, well, it's in the middle of crush, for one. It's the middle of season. Their maximum amount of water, their maximum amount of contaminant. But it's the first time you've seen air, in this big pool of water, and you're hitting all that, as I was talking earlier in the presentation. And so anyway, we discussed that if this is starting to like climb up over the freeboard, we can mist it with water, or you could actually get an anti-foaming chemical. And also we're learning at what point to run the air. We oversize everything a little bit, and he could go into, you can lean into the throttle, so to speak, and maybe we're sending too much air to it. But it turned out to acclimate, powered through this, and subsided, and it was a non-issue in the end. So I talked about the blower fire, and let me progress to that. 200 horsepower blowers, big blowers. They were supposed to start at the same time, but they were Gardner-Denver product, and Gardner-Denver blowers by Universal Blower Pack. And so we got the first one there in January, and I was there and got that one started up. So the other one didn't show up till a couple months later. And it was the one that was the second one that didn't show up as the one that caught on fire, because we weren't there to set it. We worked with the local contractor to pick it with the crane and set it and connect it. But the belts weren't double checked for alignment. And that's, again, eventually what's going to be the problem. The ponds fill, irrigate out to empty. This pond right here, there's water ponds all over the site. This is the pond we're dealing with. This is just a control panel config, hour meters, so they can, duty cycle or see what the hours are. You can go up to 6,000 hours on synthetic oil. VFD, potentiometer, just typical. Picking and setting the blower. Blowers at that view, separate control panel for each one of those 200 horsepower blowers. So then this happens. So they got it started in March, blower fire on 3/22/21. Environmental manager calls me and says, whoa, 355 hours on a brand new blower. And these are 8 belts wide. And that's going to be a key point as we look at the subsequent slides here on what happened, what occurred. So this is what it'll look like when they get to it. And it just made smoke damage, it melted things, created some heat. So what our concern was, do we have a material, or is this cosmetic or messy, or did we ruin a motor or a blower? And this site has electricians on site, maintenance staff. It's a very, very large site, maintenance people. And so our first response was, okay, is the fire, is the heat out? Yes. Does the blower and motor spin freely? This is over the phone. Yes, their guys vetted that. We said, check the oil level in the blower, pull sample for visual lab testing. There's a certain thing you look for, and it indicates if it got too hot or not. And then we had spare belts. They says we could put those on, realign and tension the belts, make sure we align the belts. They said they have blowers all over the site. They're familiar with doing that. And they used the angle irons, the straight edge against the pulleys. Replaced the air filter. We had spare air filters. The blower was restarted the same day it was discovered. They cleaned up some of the ashes, got out of the way. They had spare belts and filters. In the meantime, their second blower is running, so they're getting air to the pond. But they were only down that day. And then at 733 hours, same blower, same thing again. And we're like, what in the world is going on here? So I called Universal Blower Pack on behalf of Triple Point, and I says, send your man. We need to go out there and see what's going on. I feel like I just handed these guys the keys to a new Porsche, and it's just burning. The key don't turn on, or it doesn't go. What is going on? And we went out there. All this was, at the end of the day, we verified too that this was, and this time the environmental engineer actually come by and he seen embers, so he used his fire extinguisher and just put some more stuff in there, more things to clean up. But he wanted to make sure the wind didn't blow an ember out and start a fire somewhere. So we brought the guy from Universal Blower Pack, and we free spin the blower. There's no paint bubbling on the blower. It indicate really hot. It was kind of superficial, melted, nasty. It was just dirty. We brought things to clean up and to get it back in gear. And so here's putting the belts back on. Now that's a pretty good distance across there. And the angle iron that was used out there previously it's a two-man show. There's no way you can hold that angle iron up and look for all these contact points right here. And you got 8 belts, and you can think if you're slightly out of a line, it's different on the 8th belt on the outside versus the one on the inside. And that's turned out what to be the issue was. It was just out of line enough that you've got belts that are turning and burning and slipping, and it just was not aligned. It's not a big of an issue with a single belt or a 2 belt. You also want them aligned, but the alignment gets incredibly critical. These shafts have to be spot on parallel when you have 8 belts. And that's really what the deal was. And so each one of those, he said some guys will force all the belts on. He likes to put on 2 belts at once and work them to the back, and then 2 belts, then 2 belts. And don't And make sure you got enough slack between here so you're not really jumping it over the edge when you're putting those on. And then use their tension device tester based on what the manual says, and let's set each one of these tensions just right. And so the tension, correlates to deflection, and you push this little instrument, and there's instructions, and I carry these things. We'll be doing that one today with this Apple processor. And eventually, this is a graphic that shows that if you put a string right here and it's not going to touch this other touch point. And you got 4 touch points really at the outside of each one of these. Now, if you have a nice straight edge right here and you can see it in a smaller blower and hold it up and get a nice visual, but I will tell you this string, when you hold a string, and this was 2 guys that took us both. Now you could tie it off like that and come over with one guy, which is again with one guy is a lot easier. With string, it's very hard to see holding up a heavy piece of angle iron. You should touch, 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 touch 4 times. If you have any air right here, and when we're doing this, we're looking at it, and it was like 2 millimeter. That's not good enough. We had to get it to its touching all 4 points with the criticality of 8 belts, and we did get there. And just a final thing I want to add here is just a couple more slides. This was interesting. This was all going on close to the same time that one of the other blowers, they'd observe when they're operating simply this, looking at the blower panel, that one of them was running at X amps and the other one was X plus 5, at least 5 more amps. Why it should be this? Yeah, it should be the same. It should be like negligible. It should be almost identical, the same, or just negligible because it goes out to 2 decimal points. And the irony is, if you look at 311 was a new installation, and in 415 you had five extra amps. Like, what's going on? Do we have something going on in the system? Is it a valve, pushing head loss against the system? It was this. There was simply a lot of riprap going on. The wind blows there, and this air filter was picking all this dust up, and we simply changed the air filter out, which you would not normally think about in 4.5 week window. And it solved the problem. And so when it's fighting against trying to suck through there and it's dirty, it's just going to, it's going to work harder, it's going to draw more amperage. Couple final notes. We've been doing more and more mobile units, like in this frac trailer type of environment for ammonia and total nitrogen. And I know that we're working on one at a beef plant in Iowa right now. Here's one on the dike. This is one that we built for waste management. So this is landfill leachate. They got an ammonia issue. And so this is a mobile unit, a blower set right in front. It's fully self-contained. You can bring it in. We've done these as rentals multiple times. We did a rental for another company. They had a groundwater nitrogen contamination issue. It was a munitions manufacturer. They used nitrogen in that. And we had a couple systems, and they just said they just wanted to buy them from us. But as far as a quick turn unit that might do seasonal, or you need something soon and can't go into a big long civil capex year-long procedure, we're seeing a little bit more demand for this. And again, one's a meat processor. I think we're set up right now at. And then I'm at an Apple process. I actually took this photo this morning, and their electricians out there wiring the blowers up, the panels over here, and they just pulled all their surface air off, and we'll be putting in subsurface aeration over the next couple days. And they pulled all these old surface aerators out. Just getting odors, and just wasn't keeping up. I mean, these things can do okay when you first put them in, but when you got a deeper pond, it's just tougher. The solids pile up on it in the bottom of that pond, and either gonna have to dredge or do something else. In this event, in this instance, they're doing something else. So that's the end of the presentation, and I'll probably do an Apple update down the road. I haven't done an Apple processor yet, but to us, it's just water. What's in the water? What do you need out? What's the effluent quality you need? And we design to it. I've done frac water before. Probably the most difficult water I've ever done is frac flowback water, produced water, because you got materials compatibility issues with diesels and fuels and things. But again, it's just water. What's in it? What do we got to get out of it? What do you want the final effluent to be? So I don't know if there's any questions yet, and if we run out of time for questions, we will. Another time I did this, and there was like 25 questions we couldn't get to, so we actually answered them all and reposted it out to everybody. And I'm looking, I don't see any questions. But there will be an opportunity at the tail end to post a question, and we will answer it if we don't see it live right now, and you've got a specific question, or you want to talk about a specific project, or question something that we presented, or a claim that we made, or what have you. Here's a question coming in real quick, a couple minutes. What about maintenance? So in the wines, I'd love to talk about wine for a second because I've done several of those. As long as effluent quality is being, as far as the aerator goes, we recommend that in a 2 to 3 year window that the aerator be pulled up and pressure washed. Now the sugar beet one I showed you, the water goes up and down. They have the opportunity to do that from hydro persuading from shore, but that's the nature of most ponds don't go down like that. That was an interesting thing. The key thing is on the blower side. You need to change the oil every 6,000 hours. Belts once a year. Filters, you need to look at them pretty regularly, depending on cottonwood, dust, dander, and situations like that. Question, do you know the surface area for microbubble? I don't, but I'll bet it's many times what the surface area is for fine bubble, but I don't know the answer to that, but I would like to know. Here's a question, does the slope size get well mixed with Aries aerators? How to assure complete mix regime of the whole lagoon? Does the sludge deposit on the slope sides? Yeah, corners is, I'll tell you, when we do these dry ones, it's really nice that you can go right. We want that area right in the corner. Corners, particularly on the slopes, get overlooked. Now, I'm working on a pulp mill in Canada that has a 3.5 to 1 slope, so it's quite flat. And they weren't going to look at anybody for aeration upgrade that didn't mix those slopes. So we actually have a model that's we call the slopester that is able to go on a slope and mix in a slope. And so we're aware of that. If it's a 2 to 1, that's steep. So usually we can get that handled from the flat bottom. 2.5 to 1, 3 to 1, you're generally good, but you want to have those aerators scooted right over to the edge. You don't want to be 10 feet, 15 feet off of the edge out to the middle, because when you fill that up, assuming maybe a 10-foot level, you can reach over there. Corners is a big concern, and just make sure you lay it out properly. Can area system be installed? Yeah, in an already filled lagoon. Yes, we do. We actually provide a pontoon boat. I actually have it here. It's my own company. I sublet it to Triple Point, and they've got another one on the other side of this. I do the Western States, and we will literally go right out on the pond and come up from the shore with the aeries with the hose behind it, go out to a drop point and drop it into a wet lagoon. What do you find the various diffuser materials? We are going with the silicone right now, perform the best, but actually one of the EPDM mixes was second best. And but we're really liking the diffuser material that we actually source from OTT, the silicone material. How would you set up continual sludge removal so heavy equipment does not need to be introduced? An early question, likely. I would do subsurface air on the floor, and I don't think you kick it down the road forever, but you're going to mitigate it. Just depends. If we go to a complete mix, everything's in suspension, you will theoretically never have to deal with solids in that, other than the fact that if it's bioavailable, if it's sediment, wind deposition, sand, and the like, silica, but there's nothing anybody can do about that. If that settles in the bottom, it's eventually going to have to come out. I did a sludge judge at a winery in Central Coast, and when I got down on the bottom, I could feel it was hard, so I was twisting my sludge judge back and forth like this, and I go to pull it up, it wouldn't come out. It was just completely compacted. I was out on a little rowboat, had to go to shore and get a piece of wire. I couldn't even get through it, and it was the heavy stuff that went right to the bottom. It had probably been accumulated for 20 years. It wasn't terrible, because most of the stuff above that we could actually get at. That was, we did a volatile solid there, it was 67%. So if we can stir that up in the treatment column, we can deal with that, and it'll keep you from getting the guy into pump it out or do scraping treatment or the different methodologies they have to dredge lagoons. And did you find issues different diffuser materials? Yeah, the polyurethane didn't work very good at all. Most of the rubber DPM stuff was good. Our service barges, we've got a couple electric cranes on it. Here's another question. And then pricing, we'd have to get to some sort of basis of design to back into pricing for a job. But a little winery in California was $15,000, and Great Big Sugar Beet project was an order of $1 million. So it's everything in between. It just depends on the flow and how clean you need to get it. And that's it. If there's any additional questions, can post those in the post summary thing, and we'll address those. If there's project specific we want to talk to, we'll talk to you or introduce you to our reps in the area. And I thank you for your attention.